Okay, hello everyone. So today we're going to begin chapter 3, which is about probability. So the objectives of this chapter are to understand and use the terminology of probability to determine whether two events are mutually exclusive or whether the two events are independent, and to calculate probabilities using the addition rule and multiplication rules, and then also we'd like to talk about constructing and interpreting contingency tables. Okay, so let's get started. Key concept. The single most important objective of this section is to learn how to interpret probability values. Probability values, which are expressed as values between 0 and 1. A small probability such as 0.001 corresponds to an event that rarely occurs. Okay, and so that's the hope that we'll understand what that is. But let's talk about what a probability is. In order to do that, first we're going to talk about what an experiment is. An experiment, or sometimes called a trial, is a planned operation or procedure carried out under controlled conditions. An outcome is a result of an experiment. An event is the term used for a collection of outcomes of an experiment. So you've got outcome, that's the single result of one experiment. And an event is a collection of possible results for the experiment. Blank of an experiment is the set of all possible all possible results. This is the sample space. So this is the sample space of an experiment is the set of all possible outcomes, and this right here is just an event is a subset of that. It's a space. It's the set of all outcomes of interest. Okay. Here is an example. Simple events and sample spaces. Okay, so in the following display, we use B to denote baby boy and G to denote a baby girl. So here's the procedure. This procedure, which is kind of an odd name for it, but it is what it is. The procedure is going to be a single birth. And so in this first row, we have the example of a single birth. Okay, what's an example event? One girl. It's a set of and then the set of all possible outcomes is you can either have a boy or a girl, and that's it. And that's what happens at a single birth. Another procedure is 3 births. Oh, there's a typo there. 3 births. Now with 3 births, an example of an event would be 2 boys and 1 girl. Now notice, this is not just a result, because there's actually 3 different results that fall within this event. So this event really is a set of outcomes, because you could have boy, boy, girl, boy, girl, boy, or girl, boy, boy. Both of those result in 2 boys and 1 girl. And so that's an event. The sample space for this procedure is going to consist of 8 of these. Boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, and so on. Girl, boy, girl. Okay, and then so what's this one here going to be? This is going to be girl, girl first, girl second, and boy third. And then this one is girl, girl, girl. And so that completes that sample space of 8 different samples. And notice, how is that computed? Well, the first child that came along, there were 2 options. The second child, there were 2 options, and the third child, there was 2 options. If we multiply all of those together, multiplying, because for each one that is chosen here, for each of those, there's 2 possibilities here. And for each of those 4 possibilities, there is 2 possibilities here, and that comes to 2 to the 3rd, which is 8. Okay, finding or computing probabilities. Well, let's talk about some notation first. So we use the capital letter P as sort of a function to mean the probability of, and then we use A, B, and C to denote specific events, which are, remember, sets of outcomes. So we say P of A denotes the probability of event A occurring. Event A occurring meaning that an outcome of a single experiment is contained in the set A. What's the probability that the experiment will produce an outcome that is contained in the set A? That number is this probability. Okay, now probabilities come between 0 and 1. So 0 is impossible. 1 is absolutely certain. If it's close to 1, then it is likely. If it's close to 0, it is unlikely. And if it is 0.5, then it has roughly equal chance of happening as not happening. Okay, so possible values in the probability. So you look here at this little chart, and it relates the common expressions of likeliness. Common expressions of likeliness. Okay, now there's basically 3 approaches to finding probabilities of an event. So first one is this relative frequency approximation of probability. So a relative frequency approximation. So this is also sometimes referred to as an empirical probability. Let's see. A procedure and count. So conduct or observe a procedure and count the number of times that event A occurs. P is then approximated, and that's very important to note. This right here is the true probability, right? P of A is the true probability of the event A happening. However, that true probability, that theoretical probability, can be approximated by a sufficient number of trials. So it's the number of times A has occurred over the number of times the procedure is repeated. And so this manifests itself when it's like incidence rates, or what's the probability of being struck by lightning? Well, what they do is they take the population of the United States, and they take the number of people who were struck by lightning, and they divide the number of people who are struck by lightning by the total number of people in the United States, and that gives them some ratio, some relative frequency of being struck by lightning, and that they use as a probability. And so it's pretty small. Anyway, so there's also a classical approach, or perhaps a theoretical approach to probability, and this requires events being requires equally likely outcomes in order to compute this. So this is really computing it. If a procedure has n different simple events that are all equally likely, such as rolling a particular number on a symmetric cube, a die, right? Each face is very similar to the other, and so there's no reason that one face would have a greater probability of being of landing face up than any other. So if the procedure has n, then you can count the number of ways. So it's the same thing, the number of ways that A can occur versus the number of different simple events. So the size of the sample space. Okay, caution. When using the classical approach, always confirm that the outcomes are equally likely. Don't assume that they're equally likely. You need to support that with some sort of rational argument. Okay. And then the third common approach to finding probability is subjective. Subjective. So P of A, the probability of event A, is estimated by using knowledge from your own experience of the relative circumstances. So for instance, because nobody I know has won the lottery. Nobody I know has won the lottery. I suspect that the probability of winning the lottery is quite small. Something like that, right? Is small. Okay. Rounding probabilities. How do we round probabilities? When expressing the value of a probability, either give the exact fraction or decimal. That would be fine. Give the exact fraction or decimal, or you can round to 3 significant figures. 3 significant figures. And then there's a suggestion here: when a probability is not a simple fraction, such as 2 over 3 or 5 over 9, express it as a decimal so that the number can be better understood. So, yeah, that way you have a good idea. So like if it's something like 241 over 733, write that as a decimal, because we really don't know how big that was. Is that it's less than a half, but how much less than a half? Is it more than a third? I don't know. So that's helpful. Okay, the law of large numbers states that as a procedure is repeated again and again and again, the relative frequency probability of an event tends to approach the actual probability. And so that's sort of a theoretical guarantee, in a sense, under certain conditions, that as we repeat it again and again and again, the relative frequency approaches the actual probability. And that's huge. That allows us to say with some degree of certainty that the probability of such and such an event is this. We don't have a theoretical means of determining that probability, but we do have a lot of data, and we can leverage that data to estimate or get a good idea of the actual probability. Okay, this comes with a caution, though. The law of large numbers applies to behavior over a large number of trials and does not apply to any one individual outcome. So what that means is that the probability of winning a coin flip is 1/2 in general over a large number of trials. However, if you're doing this individually, right, and you're sitting there, you're flipping the coin, and you lost the last 5 coin flips, that doesn't mean that the 6th one is going to end in your favor. That's something called the gambler's fallacy. This idea that I'm due to, it's got to be this way in order to respect this average, 1/2 thing. But the truth of the matter is that every coin flip is completely individual, and it does not care what happened before it. So this idea that you're due is a fallacy. Okay. Also, if we know nothing about the likelihood of different possible outcomes, we should not just assume that they are equally likely. Okay, now let's talk about combining events. So events can be combined to make new events. So OR is a way to do that. OR means that the outcome is in A or B or both. So the probability of A or B is that it's in A or B or both. So here's an example. So let's say I'm rolling a 6-sided die. I've got my sample space is 1 through 6. My event A, I'm going to define as rolling an odd number. So that's going to be 1, 3, or 5. My event B is going to be rolling a number that's strictly less than 3. And so that includes 1 and 2. So what's the probability? And so what is the event, A or B? Well, that's going to be all of A. You see A is represented there, and all of B, both represented there. And so what's the probability of A or B? Well, we can use the classical approach to determining the probability. There are 6 possible outcomes, 4 of which are within the set AB. And I'm not going to simplify, because if I keep it as 4 over 6, you see exactly where that number came from. If I write 2 over 3, it obscures where that number came from. So I'm just going to keep it that way. All right, so A and B. The probability that an outcome is in A and also in B, both, I don't know what that one's about. Let's cross that out. Both, maybe I meant to do a capital one, an explanation point. Okay, example. In rolling a die, here's our example as before. So same A and same B. The set A and B, sometimes written A intersect B, is 1. And the probability of that is going to be 1 over 6. Because there's only one way that can occur, and that's if you roll a 1. No other way can you get a number that is strictly less than 3 and also odd. So both need to be satisfied when it comes to and. Okay, now there's something called conditioning. This is another way of combining events. This is the probability that the outcome is in A. Okay, so the outcome is in the set A, given it is already in B. Okay, so given B. So this is pronounced, this thing right here. This is pronounced probability of A given B. And that's what you say to communicate this symbol. All right, let's go back to our example here in rolling a die. So the sample space is the same as before. A and B are both the same as before. Now, what we want to know is what A given B is. Well, the set of all outcomes of A, given that B has already occurred, is just going to be 1. So notice, if B has occurred, there is no possibility of 3 or 5 because B has occurred. So it's either 1 or 2. 1 is a possibility, right? So that's the only possibility that can be an A given B has occurred. Now, what's the probability of that? Okay, that is going to be, and the new sample space is B. So given B has occurred, the new sample space is either 1 or 2. And so that is 2 in size. There's only 2 possible outcomes given that sample space. Now, how many possible outcomes are in A? 1. Okay, so if we know that B has occurred, it's either a 1 or a 2. What's the probability of it being an A? A half. 1 is in that condition, 2 is not. And so that's 1 over 2. So that's the conditional probability there. We'll talk more about that later. Okay, complement. A complement written A prime or A complement or A apostrophe is the probability that the outcome is not in A. So this is the opposite. It's not in A. So I have, in my same example, rolling the die, event A is rolling an odd number. The complement of A is rolling an even number. So this is the opposite. So it's 2, 4, 6. The probability of A is going to be 3 over 6. Now, look at this. The probability, what's the probability of A and A complement? So something being in A and A complement. Well, that's impossible. You can't have something in A and its complement because the complement is everything not in A. What is the probability of A or A not? Well, that covers everything. That covers all of it. It's the whole sample space. Okay, identify significant results with probabilities. Now, this is super important when it comes to hypothesis testing. I can't stress this enough. this is the sort of thinking you are going to engage in quite heavily when it comes to hypothesis testing. If under a given assumption, okay, so there's a given assumption, which we will later refer to as the null hypothesis. If under a given assumption, the probability of a particular observed event is very small, and the observed event occurs, okay, so the probability, if the assumption says that this event should not happen, it's very, very rare, and it happens, well, what are you going to do? And the event occurs, either it is significantly less than or significantly greater than, something like that. So that refers to this small probability. Okay, so we'll talk more about that. If it occurs, so it's significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is false. Is false, or not. Perhaps a better way to say it would be not accurate. So there it is. Okay, let's take a look at this. So, right. So if it's significantly less than or significantly greater than what we would typically expect with that assumption, then the assumption is most likely going to be false. If somebody tells me, Jared, it's super rare to see a unicorn, and then I just happen to step out my door and I see a unicorn there, I'm going to reject that null hypothesis. No, it is not rare to see a unicorn, because look, there's one right there in front of me. And yeah, and if there was one right there in front of me, how could it be so rare, All right, identifying significant results with probabilities. Okay, so we have this, so before now we have identified significance of a result by being 2 standard deviations beyond the mean. This is based off of the range rule of thumb. There is another way of determining or defining an event as significantly high, and here it is. So a significantly high number of successes is going to be this: X successes among N trials is a significantly high number of successes if the probability of X or more successes has a is small, is rare, is 0.5 or less. I'm just going to talk about this more in class. That is, but I wanted to see, I want you to have it in writing. That is, X is a significantly high number of successes if the probability of getting that many or more successes is really quite low. All right, and then there's the same idea here with something that is significantly low. If the number of, X successes among N trials is a significantly low number of success if the probability of X or fewer successes is very, very small. And so that's how we know it's low. And I'm going to explain that more in class. Okay. So for now, let's look at section 3.2, which is independent and mutually exclusive events. Mutually exclusive means that the events cannot happen at the same time. Like the complement, a set and its complement cannot happen at the same time. Those are called mutually exclusive, and we see an example of that here. The probability of A and B occurring when they're mutually exclusive is 0. There. All right, independence. Okay, so independent. So if for events A and B, the probability of A given B is exactly the same as the probability of A, the fact that B happened did not change the likelihood of A occurring. It did not change it at all. That's independence. It also manifests itself here like this. If A occurs and it does not change the probability of B occurring, then they're independent. And basically, if the probability of A and B occurring is the product of the two probabilities, then they are independent. They just don't mess with each other. Okay, here's an example now. If I have two chips, and a red one and a blue chip, and I flip them, I just flip them each once. The sample space are these four outcomes. Remember, 2 for the first one, 2 possible ones for the red chip, 2 possible ones for the blue chip, and that's 4 total possibilities. And let's say that event A is going to be a red heads. So the red chip is heads. So that's the event A. B is going to be blue heads. So that's heads there. So that's B. Okay, now the red and blue chip are not connected in any way. They're not tied together. They're both allowed to flip freely, and they do not depend on each other. So we would expect these to be independent. Now let's just see if that follows. So the probability of A and B occurring is the probability, so A and B, so that's the intersection, so that's this one right here. That's the probability of HH. And that is equal to a fourth, because that's 1 out of the total sample space, which is 4. Now, you'll observe that a fourth is the same thing as 1/2 times 1/2, which is numerically equivalent to the probability of A occurring, because notice the probability of A has 2 outcomes of interest out of 4 total, and so that's 1/2, and the same can be said for B. So this, okay, so this follows. This is independent events, because you can split up the intersection. Okay, now independent can also be used to define independent trials. So if two sets are independent, if the outcome of one does not affect the outcome of the other, and so that's the idea. And so generally speaking, if the sets refer to a different trial that does not depend on the trial before it, then they're going to be independent. Okay, see, so when it comes to sampling, you can have independent or dependent sampling. It's going to be independent if each time you sample, you replace what you already sampled, so that you're dealing with a full deck, so to speak, to begin with. So if each member of a population is replaced after it's being picked, then the member has the possibility of being chosen more than once. I guess that's sort of a drawback when it comes to surveying people. But when a sampling is done with, and that's done with replacement. Now, when a sampling is done with replacement, then events are considered to be independent. There's no dependence between two samples. Without replacement, though, that changes things. When a sampling is done without replacement, each member of the population may be chosen only once, will be chosen only once. Will be chosen at most once. In this case, the probabilities for the second pick are affected by the result of the first pick. There are less possibilities. That changes the denominator. Okay, the events are considered to be dependent. Okay, so let's just take this little example. Suppose you are sampling with replacement. So that means I pull a card randomly. I get a 5 of clubs. 5 of spades. And then I put that back in and draw again, and I might draw that again. Okay, that's with replacement. But the probability of each draw was 1 out of 52, because there were 52 possible cards. If I did not replace, and I draw without replacement, my first draw is 5 of spades, that is now no longer a possibility for my second draw. So the probability of getting a particular thing, the second draw, is going to be 1 out of 51. The denominator changed. It's not the same as it was before, and that means that it affected it. So there's a dependence, and those are dependent events. All right, everybody, that's it. Have a wonderful day. Good luck on the homework and the quiz.